Hi, welcome back. In this video, we're going to talk about how to factor polynomials using the rational root theorem. Now, we've factored polynomials before, like quadratics, cubics. We've factored different polynomials, but these are going to be particular polynomials that you cannot do the things that we've done with cubics. So we'll have a part 1 and a part 2. Part 1 will be focused on cubics. Now, the two things that we've done so far for factoring cubics have been factoring cubics using the SOAP method, which is when you subtract two cubics. Right? We use the same, opposite, always positive method. And you can look at a video for that. We've also factored cubics using something like, say, 2x squared. And then we use grouping method where they both have an x squared in common, right? An x plus 2. And then maybe we have a, say, 4x plus 8, right? Where this side has a 4 in common, and when you factor out the 4, or divide everything by 4, you're left with x plus 2. And then you realize both of these groups have an x plus 2 in common. Yeah? And then when you divide both by x plus 2, we're left with x squared plus 4, right? We have two different factors given the grouping method. So grouping and SOAP method are the methods we've discussed so far. Today we're going to talk about a different method. What happens when you cannot do grouping as an option, right? And we talk about this as a rational root theorem. Now, a rational number is just a number that can be expressed as a fraction. As long as you're not dividing by 0, right, you can write any number as a rational number. And we're going to be dealing with rational numbers here to find the factors of a cubic polynomial. All right, well, part 1 will be focused on cubics, and then in my next video, part 2 will be focused on to the 4th power. Right, this will be part 2, and we could even go higher than to the 4th power. We just do the same method that I will be showing you in the next video, over and over again until you get all the powers you need. All right, let's talk about to the 3rd power. Let's do a couple of examples. Here's our first example. Right? Notice how we cannot factor this through grouping method. If I split this into two parts, I won't have a common factor on the left and on the right that they both share in common. Right? So what I want to do for the rational root theorem, we're going to label this last number, the last constant, as p, as a constant, and the leading coefficient as q. Now, the ratio of its factors will create a root, or possible roots for this cubic function. So, first thing we want to do is we want to look at the factors of p and q. Right? What are the things that multiply to give you -1? Well, for p, the factors of p are going to be 1 times -1. Right? Or plus or minus 1, if you want a shorthand of that. What are the factors of 5? Well, 1 times 5 can multiply to give you 5, and -1 times -5 can also multiply to give you +5. Now, a combination of these, right, for p and for q, q is in the bottom and p is on top. The combination of these, there's a lot of combinations that we have. We actually have 8 combinations. There's 2 possibilities per p, there's 4 possibilities for q. When you multiply 2 times 4, we're going to get 8 different combinations. Our goal is to mix match, right? 1 over 1, 1 over 5, 1 over -1, 1 over -5. Our goal is to mix match all the possible combinations, and those fractions will create at least one x-intercept, or one root. So let's first label the possible combinations of p and q. These are the possible combinations of p over q. If 1 on top is positive, I can divide it by 1. I can also divide it by 5. I can divide it by -1. And I can divide it by -5. there are four unique combinations where 1 is the numerator, right? Now, if -1 was the numerator, I have 4 other unique combinations, right? Or I have 4 combinations that I can do with -1 as a numerator and with +1 as a numerator. Now, as I simplify these, I'm going to end up getting unique combinations. Remember how I said that we have 2 on top and 4 on the bottom? 2 times 4 gives me 8 possible combinations. Now, some of these possible combinations are really the same number. They're repeated. So let's look for the unique rational roots that we're going to get. And to do that, we divide the numbers. 1 divided by 1 is really just 1. Now, I can divide 1 by 1 to get 1, and I can also divide -1 by -1. So these are actually being repeated. It's the same root, the same solution, with just negatives or positives, right? Another possible combination here is 1/5. I can divide both positive numbers or both negative numbers. They both result in 1/5 as an x-intercept. I can divide 1 by -1. That's -1. And I can divide -1 by 1, and I also get -1. And then lastly, as you can see, 1 over -5 is -1/5. And -1 divided by 5 is also -1/5. So out of 8 possible combinations, we have 4 unique numbers, right, that are going to be roots. Now from these 4, 1, 2, or maybe all of them, well, at most 3, right, will be the x-intercepts for this graph. So the first thing we want to figure out is this part. This is one of the most important components. Can I find the combination of factors between p and q, and when I divide the two numbers, I create these rational numbers, these fractions. And then can I look at the unique combination of fractions, and those are going to be my possible x-intercepts or possible roots for that cubic. How do I identify whether or not these are x-intercepts? Well, we have to divide the number into the polynomial and see if we get a remainder. Think about this when you're thinking about remainders. Is 2 a factor of 7? No, because if we divide 7 by 2, 2 goes into 7 3 times with a remainder of 1. Since there's a remainder, we can say that 2 is not a factor of 7, right? Now, is 2 a factor of, say, 10? Well, if we do 10 divided by 2, we get 5 with 0 remainder. Whenever we get a 0 remainder, we can say that the number is a factor of the other, right? And you can rewrite 10 is really just 2 times 5, which is why they're factors of 10. So our goal here is to figure out, are any of these solutions of this problem, of this polynomial, meaning do any of these fit in perfectly with 0 remainder in the problem? So we're going to use synthetic division to be able to find these values. If you want a recap of synthetic division, go to my previous video. I made a video on just synthetic division. And I made a video also on long division if you prefer. Let's try out the first value here, 1. So I'm going to plug in 1, and I want to do long division or synthetic division with the original polynomial. 5, -11, 7, and -1. I'm using synthetic division because it's a little bit faster and it requires less space, right, for me to be able to show you how to solve it. When I'm doing synthetic, I bring down the first value and I multiply. 1 times 5 is 5, and then I add these, I get -6. 1 times -6 is -6. When I add these, I get +1. 1 times 1 is 1, and when I add these, I get 0. Now, since my remainder was 0, I have found a solution. X equals 1 is a solution of this graph, or of this polynomial. If I were to graph that, 1 is definitely an x-intercept. And the remainder 0 verifies that that's the case. Now, since I'm dividing a cubic by a 1 solution, I'm going to be left with what? What's x cubed divided by x? I'm going to be left with x squared, meaning my the remainder of my synthetic division is a quadratic, right? This is really going to be simplified down to 5x squared minus 6x positive 1. That's what that represents. Now the x equals 1 was a solution. How do I find the factored form of that solution? Well, I bring the 1 to the other side with the x, and the factored form of the solution is really just x minus 1. So these are my two factors of this cubic polynomial. The next thing that I want to do is I want to check to see whether this polynomial is factorable. I have a quadratic. Let's check to see if 5x squared minus 6x plus 1 can be factored further. I have 5x times x is 5x squared. 1 times 1 is 1. When I cross multiply, I get 5x and 1x. And the only way to get a negative 6 from these two numbers is if they're both negative. Meaning that my factors were 5x minus 1 and x minus 1. So I can see that I have three factors. My x minus 1 is there from before, and now this quadratic was broken into two further factors, 5x minus 1 and x minus 1. This is my function in factor form. See how I have my three factors? Now, since the x minus 1 is repeated, I can technically write this even shorter. I can combine these x minus 1 and write it as squared, right? There's two of these exact same terms, and I have a 5x minus 1. This is a little bit more condensed version of the factored form of a polynomial. Now, once we find the factors, we can find the x-intercepts, and we'll talk about that later in another video. How do we graph something like this? We would want to look at the roots or x-intercepts that come from the factors. So technically, this problem could be broken down into three parts. First, find the unique rational roots that are going to exist, right? Find the factors of p and q, and then find all the combinations of those. Simplify the combinations to find the unique possible x-intercepts. Then use synthetic division to find a 0 as a remainder. Had 1 not worked, I would have gone with 1/5. Or I would have gone with my whole numbers, actually. I would have tried the same thing with -1 to see if I got a 0 remainder. If that didn't work, then I would have gone to the fractions and tried it until one of them gives me a 0 remainder. From these four, at least one will work. That's what this rational theorem is about. It'll create rational numbers where at least one of them will be the root of that cubic polynomial. All right, let's try another one. Let's put some more practice into this. Remember to label this one as p and the leading coefficient as q. Our goal is to find the factors of p and q. P is the number over here. To get -2, I'm going to multiply 1. I can multiply 1 times -2, or I can multiply -1 times 2. Yeah. In the denominator for q, to get +2, I can multiply 1 times +2, or -1 times -2. Right? So basically I have plus or minus 1 and plus or minus 2. If you want the shorter version of this, you can just write it like this notation. They're the same thing. I have a plus and a minus 1 in the bottom, and then I have a plus and minus 2 in the bottom as well. You can write it where they're all written out, or you can write them in a more condensed form. Either way, my goal is to find the combinations of all these fractions, right? Since I have 4 numbers on top and 4 in the bottom, 4 times 4 will create 16 rational roots. Right? It'll create 16 fractions when you're combining them. So my possible p over q fractions are going to be, well, what happens when 1 is positive on top? If 1 is positive on top, I can divide it by 1. I can divide it by 2. I can divide it by -1, and I can divide it by -2. If the number on top is, say, -1, say this one, I can divide it by 1, by 2, by -1, and by -2. And I can go through this process for all the numerators, right? If -2 is my numerator, I can divide it by 1, by 2, by -1, and by -2. And if 2 is my numerator, I can divide it by 1, by 2, by -1, and by -2. Notice how there's 16 possible combinations, right, of P and Q. These are all the possible mix matches that I can create from these two factors. The factors of -2 on top and the factors of 2 on the bottom. Now, all of these are going to simplify to just unique P over Qs. How many unique values do I have from 16? Well, let's simplify the fractions. 1 divided by 1 is just 1. I can get a 1 when they're both positive, when they're both negative, when I'm dividing two negative numbers, like -2 divided by -2, and when I'm dividing 2 by +2. All of those result with 1. What about 1/2? How can I get 1/2? I can get 1/2 by dividing both positive numbers, both negative numbers will also give me 1/2. I can get a -1 when I divide the bottom by a negative or the top by a negative. I can divide the 2, as long as one of them is a negative, I'll get a -1. And the denominator could be a negative. 2 divided by -2 is also -1. And then lastly, let's see, not lastly, but I can also get -1/2 as a possibility when the bottom is a negative or the top is a negative. I can also look at -2 as a solution. Divided by 1 or divided by -1, both of those give you a -2. And I can finally get a +2 when you divide both positive or both negative, right? 2 divided by 1 and -2 divided by -1 is also 2. So 16 possible fractions came down to 6 possible x-intercepts. Now I can start checking all of them out. Which one of these will result in a zero remainder for the original problem? Let's start with 1. I start with 2, -23, -16, and -2. Let's check these out. 1 times 2 is 2. When I add these, I get -21. 1 times -21 is -21. And as I add these, I get -37. 1 times -37 is -37. And notice how these two don't add up to 0. It's -39. I'm looking for a zero remainder. So 1 is not a solution of this original polynomial. Let's try it again with, let's say, -1. Try the same method, right? Synthetic division. I'm going to try using the whole numbers first and then maybe the fractions, or a few whole numbers and then the fractions. Let's try it with -1. -1 times 2 is -2. This changes to -25. -1 times -25 is +25. When I add those, I get a +9. -1 times 9 is -9, and that's -11. That didn't give me zero remainder. So that didn't work out. You can try more numbers, or let's go back to try the fractions. Let's give it a whirl here. What would we get with a fraction of 1/2? 2, -23, -16, and -2. I'm going to keep repeating this process until I find a zero remainder at the end. Let's bring down the 2. What's 1/2 times 2? Half of 2 is just 1. And if I add these, I get -22. Well, what's half of -22? -11. When I add these, I get -27. Half of -27 is -27 halves. Is that going to add up to 0? No, that does not give me zero remainder. About a -1/2. Let's try -1/2. Same problem. The original cubic polynomial will be use synthetic division. So let's bring down the 2. -1/2 times 2. Half of 2 is 1, but since we're multiplying it by a negative, it'll be -1. This adds up to -24. Half of 24 is 12. And negative times a negative is a positive. So these add up to negative 4. Half of 4 is 2, and negative times a negative is a positive. And when I add these, see how I got a 0 remainder? We found our solution. It just took us 4 times to get to x equals negative half. Just took us a little bit, right? So let's interpret our solution now. Since we're dividing a cubic polynomial by a single x intercept, we're going to be left with a quadratic. This is a quadratic, 2x squared minus 24x minus 4. And now this 1/2, since x equals negative 1/2, we're going to bring it back into its factored form. So I want to change this problem back into its factored form. Since I'm dividing by 2, I'm going to multiply both by 2. I have 2x equals negative 1. And since I am subtracting 1, I'm going to add 1 to bring it to the other side. I'm going to clear this up a little bit. I have 2x plus 1 equals 0. This is the factored form of x equals negative 1/2. So I can interpret this solution as a 2x plus 1. Now my only question is, can I factor this further? So let's check it out. I have a 2x plus 1. My first factor is already complete. My second one, what do I notice about all of these 3 terms? Well, they're all divisible by 2. Right? If I divide everything by 2, I'm left with x squared minus 12x minus 2. Is this factorable? Can you create 3 columns where they cross multiply to give you a negative 12? And the answer is no. So this is my simplified cubic in factored form. Right? In this scenario, we went through 16 possible fractions and we reduced them down to 6 problems, 6 unique solutions that could potentially be solutions for this polynomial. We ended up trying out a few until we found one that gave us a 0 remainder. This iteration might continue for a while. But don't worry, I won't give you problems that will go beyond 6 different possibilities. If you do get some that are beyond 6, test out 6 of them. Test out some whole numbers, test out a few fractions. You should be able to find your solution within a handful of these. We're looking for a 0 remainder. That's what creates our factors. Alright guys, I hope this has helped. Don't forget to like and subscribe. And if you have any questions, just please let me know. We'll calculate later.